Welcome. The topic we'll be discussing in this lecture is deadlock detection. So far we have discussed what is a deadlock, how to uh, prevent deadlock, how to avoid deadlock. So the topic we'll be discussing in this lecture is deadlock detection. That is, if you are not preventing or avoiding deadlock, then the third method is you'll allow the system to go into the deadlock and then it should be recovered. So in that case, we have to detect whether the system is in the deadlock state or not. We have to detect whether the system is in the deadlock state or not. Okay. So we allow the system to enter the deadlock state and then apply the detection algorithm. If deadlock is there, then we have to use some recovery scheme to come out of the deadlock state. If so, as so if there is if there is only one instance of each resource type, again this deadlock detection is done in two cases. The deadlock detection is algorithm is work. We have two versions of deadlock detection algorithm. The first version will be applied when there is only one instance of each type of resource. If there is only one instance of each type of resource, then we apply the first type of algorithm. Okay, so which is by using a weight graph. The first type of algorithm is by using the weight graph. Okay. Whereas the second type of algorithm will be used when there are several instances of a resource type. Okay, so let us discuss the both the cases. So first let us start with uh, so I think the point is clear. So that we have two versions of deadlock detection algorithm. The first version or the first type of algorithm will be used when there is only one instance of each type of resource. And this is done through a graph, and this graph is called as weight graph. This is done through a graph, and this graph is called as weight graph. Weight graph is actually a variation of resource allocation graph. Weight graph is a variation of resource allocation graph. Okay. In a weight graph, the nodes represents only processes. In a weight graph, the nodes represents only processes. In a resource allocation graph, the nodes can be either process or resources. Whereas in a wait for graph, the nodes represents only processes. Okay. So if there is something like this, Pi arrow Pj, that is if there is an edge from process Pi to Pj in the wait for graph, if there is a edge from the process Pi to the process Pj in the wait for graph, then it means that process Pi is waiting for a resource that is currently being held by the process Pj. Okay, in the wait for graph, if there is an edge from process Pi to Pj, then it means that process Pi is waiting for a resource that is currently being held by the process Pj. Okay, so so this so this wait for graph will be used only when there is single instance of each type of resource. So the operating system, or what it should do in the sense, it should periodically, so the operating system will periodically invoke the wait for graph algorithm to check if there is a cycle or not. So if there is a cycle in these nodes, okay, if there is a cycle exist in the periodic graph, in the wait for graph, then it means there is a deadlock. Okay, so basically the wait for graph should be constructed, and in the wait for graph, if there is a cycle, then it means there is a deadlock. And this graph requires an order of n square operation. Graph requires an order of n squared operation, where n is the number of processes. Let us discuss this with an example. Consider this particular thing. So this is actually a resource allocation graph. This is actually a resource allocation graph. There are 5 processes and 5 resources: P1, P2, P3, P4, P5, and R1, R2, R3, R4, R5, 5 resources. Okay. So this is the state of the process. So, so here you can see process P1 is holding the resource R2 and it is waiting for the resource R1. Okay. And R1 is held by P2. R1 is held by P2 and it is waiting for the resource R3. R3. Okay. And R3 is also waiting for the resource. Sorry. Uh, process P2 is waiting for the resource R3. It is requesting the resource R3 and R3 is held by P5 and R3 is held by P5. Okay. And P2 is also requesting the resource R4. P2 is also requesting the resource R4, whereas R4 is held by P3. Whereas R4 is held by P3. And P3 is requesting the resource R5. P3 is requesting the resource R5, whereas R5 is held by P4. P2 is also requesting the resource R5. Okay. And P4 is requesting the resource R2, where R2 is held by P1. Okay, this is the normal resource allocation graph which we know. Now from this resource allocation graph, you can construct the wait for graph. How do we construct the wait for graph? In the sense, just collapse all the resources whenever there is a what do you call, whenever there is a connection from one process to another process, you can then collapse that resource in between. Here we can see there is a connection from P1 to R1 and then R1 to P2. So remove this resource R1. So then you got P1 to P2. Similarly, from there is P2 to R3 and R3 to P5. So collapse this resource R3. So you'll get P2 to P5. Okay. Then P2 to R4 and R4 to P3. So collapse this R4. So you'll get P2 to P3. Okay. Right. So all these we got. Similarly, P3. P3 to R5 and R5 to P4. So collapse R5. So we'll get P3 to P4. Okay. Similarly, P2 to R5 and R5 to P4. So again, we'll have P2 to P4. So P2 to P4, right? And P4 to R2 and R2 to P1. So collapse R2. So we'll have P4 to P1. Okay. So in this, so this is the corresponding wait for graph. This is the corresponding wait for graph for the given resource allocation graph. So first we have to construct the resource allocation graph, and then the operating system should keep on check whether there is a cycle in the resource allocation graph or not. So what this resource allocation graph means, it says that process Pi is waiting for a resource which is being held by P2, and process P2 is waiting for a resource which is being held by P5, and P5 is waiting for a resource which is being held by P3, and P3 is waiting for a resource which is being held by P4, and P4 is waiting for a resource which is being held by P1. So there is a cycle. So there is a cycle. So if there is a cycle, then wait for graph says that there, if there is a cycle, then the wait for graph will confirm that there is a deadlock. Okay. And wait for graph is applicable only if there is single instance of each resource type. Right. So this is how deadlock is detected by using wait for graph when there is one instance of each resource type. Okay. Next, let us see how to detect deadlock when there are multiple instances of each resource type. When there is more than one instance of each resource type, how can we detect deadlock? Okay. See, this algorithm is very simple. It is very similar to the safety algorithm. or the banker's algorithm, which we have discussed. It is very similar with slight difference. Okay. Here also we maintain one vector and two matrices. There is a vector available which says how many resources are currently available. So it is same as that we used in, it is very similar as what we used in uh, banker's algorithm. So if available of j is equal to k, then it means that currently k instances of resource j is available. If available of j is equal to k, then it means that currently k instances of resource j is available. So basically this is a vector of length m which indicates the a number of available resources of each type. Okay. And there is a matrix called allocation matrix of size n cross m, where n is the number of processes and m is the number of resources. Okay. So allocation of, let me call as alloc just for short. So allocation of I comma j equal to k, allocation of ij is equal to k means, it means that currently k instances of resource j is allocated to process I. Currently k instances of resource type j is allocated to process I. I represents process, j represents resources, k represents how many instances. Currently k instances of resource type j is allocated to process I. Okay. And it maintains another matrix called request matrix, which is also of size n cross m, where n is the number of process and m is the number of resources. Request of I comma j equal to k means, request of I comma j equal to k means currently process I is requesting, currently process I is requesting k instances of resource type j. Process I is requesting k instances of resource type j. Okay. So these are the two matrices, and this is the one vector this particular algorithm uses, which is used to detect the deadlock if there are more than one instance of each resource type is available, right? So in Banker's algorithm, other than this, we also use max, and also we use need, but those matrices are not used in this particular algorithm. Okay. So, so this detection algorithm, so there is no specific name. This is just called as a detection algorithm with multiple instances of resource type. So let us go through the algorithm. The algorithm is very similar to our safety algorithm, which we have discussed in Banker's algorithm. Okay. So we maintain two vectors. One is work and finish, each of length m and n, where m is the number of resource and n is the number of process. Work is assigned to available. This first step is very similar to that of Banker's algorithm. Banker's algorithm's safety algorithm. Okay, that is available is assigned to work. Now both are same, right? So available contains list of resources that are currently freely available with the operating system. So work also contains the same thing. And then for I is equal to 1 to n, for all processes, for all, so there we numbered the process from 0 to n minus 1. Here we are numbering from 1 to n. Okay. If allocation I not equal to 0, allocation contains what? How many resources are currently allocated to process I. Okay. So allocation I means for the process I, is there any resource currently allocated or not? If some resource is already allocated, it means the process is working. It has not yet finished. So finish of I is equal to false. Okay. Otherwise, we are setting finish of I is true. See, when this allocation of I will be equal to 0, only if the process has completed execution. Otherwise, it will have some or other resource, right? So, so if some resource is allocated already, then the process is working using that resource and it is doing some task. So it has not finished. So finish is false. If no resources are allocated, then it means that you can assume the process is finished. It has completed its job. So finish of I is true. So the next step is In Banker's algorithm, in the first step, we have not checked this. We have just mentioned finish of I is equal to false for all process. The same thing also we can do here. Nothing wrong in that. Here we are adding one more check. Based on this check, we are doing this, right? And then find an I such that find an index I, that is a process I, pi, such that finish of I is equal to false, that is the process has not yet completed, and request of I is less than work. That is whatever it is currently requesting is less than or equal to the available resources, because work is nothing but equal to available. Okay. If such a process is available, then go to step 3. Otherwise, go to step 4. So this step, if you see, it is very similar to safety algorithm. There is no change at all. In step 3, what we are doing, if you find a process which is for which finish of I is equal to false, if you find a process for which finish of I is equal to false, and if you find a process for which finish of I is equal to false, and the and request is less than work, then work is equal to work plus allocation of I. Then it means that whatever the process request, you the operating system allocates that particular process, that particular resource to that particular process, and we assume that process completes all its tasks, and it releases all the resources. So we are making work is equal to work plus allocation. That is, we assume that process pi has received all the resources that it has requested, and it completed its job successfully, and it has released all the resources that it were holding. So work will become work plus allocation. Okay. So work will become work plus allocation, right? And then go to step 2. Like that, you identify all such process which are not finished, and request is less than work, and keep on doing that. If you are unable to find such a process, then go to step 4. In step 4, you check if there is at least one process for which finish of I is equal to false, then it means the system is in deadlock state, because you are unable to find a process, because we are unable to find a safety sequence. Basically, this is a safety algorithm. So finally, if finish of I is equal to false for some process, then it means that we are unable to find a safety sequence. Okay. If uh, if finish of I is equal to false, then it means that pi is deadlocked. Okay. So whichever the process finish of I is false, it means those processes are deadlocked. Okay. So this is how this algorithm is defined. It is very similar to the safety algorithm. There is no change at all. Only thing is, here the purpose for which it is used is different. Here it is being used to detect the what you call, to detect the deadlock. Okay. So this is how deadlock detection works. And this algorithm requires an order of m into n square operations to detect whether the system is in the deadlock state or not. Let us now discuss this with an example. Assume there are 5 processes P0 to P4 and 3 resource types A, B, and C. Currently, there are 7 instances of A is available with the operating system, 2 instances of resource B is available, and 16 instances of resource C is available. And this is the snapshot of the system at time T0. That is, process P0 is assigned with 0 instance of resource A, 1 instance of B, and 0 instance of C. And P1 is assigned with 2 instance of resource A, 0 instance of B, 0 instance of C. And P2 is assigned with 3 instances of resource A, 0 instances of resource B, and 3 instances of resource C, and so on and so forth. It continues. Okay. And this is the request. Here we don't use max and need. This is the current request. P0 is requesting 0 instance of resource A, 0 instance of resource B, and 0 instance of resource C. That is, it is not requesting anything. P1 is requesting 2 instances of resource A and 2 instances of resource C. P2 is not requesting anything. P3 is just requesting 1 instance of resource A, and P4 is just requesting 2 instances of resource C. And this is the available state. Available is 0. That is currently no resources are available with operating system, because totally operating system has 7 instances of A. So if you count this, 2 plus 3, 5, 5 plus 2, 7. All 7 are allotted to various processes of resource type A. Similarly, there are 2 instances of B, and those 2 are already allotted to some processes. Resource type B is already allocated. And there are 6 instances of resource C, and 3 plus 1, 4 plus 2, 6. All the 6 instances of resource type C were also already allocated to few processes. Okay. So currently operating system is not holding any resource. Currently operating system is not holding any resource. Okay. At this point of time, if you say actually the system is in a safe state, because there is a safe sequence, so the system will not result in a deadlock if you apply that algorithm, because this is what there are multiple instances of each resource types are available. So if you just apply our previous algorithm which we discussed to detect the deadlock, it will return finish of I is equal to true for all processes, because all processes can be completed, because there is a safety sequence, and this is the sequence P0, P2, P3, P1 and P4. Let us understand this. So it means first P0 will be completed. If P0 finishes, then it will release one resource which it is currently holding, that is B. P0 does not need any resource to complete, okay, because it is not requesting anything, it is holding only one resource B. So now the available resource with the operating system will be 0, 1, 0. One resource of B is available. Okay. After that, P2 will complete. P2 also not requires anything. So just after some times it will complete. After completing, it will release 3 resources of A and 3 resources of C. So now the available resource with the operating system is 313. It is 3 instances of A, 1 instance of B and 3 instances of C. Now we have to, now next to the in the order we have P3. P3. So if you take P3, P3 needs one more instance of resource A to complete, because it is requesting one more instance of A. So if you give one more instance, the operating system should give. Can it give? Yes, it can give, because it is having. Request is less than available, so it can give. So if one instance is given, then this will become, the available will become 213. Available will become 213. If one instance of resource or A is given, then the available will become 213, and this will become 0, because no more P3 needs any resource. Okay. But after some times, P3 will complete, because P3 now got all the resources, so P3 will complete. Then P3 will release all the resources, that is, it will release 2 resources of A. So already operating system is having 2 resources of A, so 2 plus 2, and P3 releases this 2, so it will become 4. So then once P3 completes, operating system will have 4 resources of A, and it will release one instance of B. So operating system will have 2 instances of B, and it will release one more instance of C. So operating system will have 4 instances of C. So 4 to 4. Okay. After that, P1 should be executed. So P1 needs 2 instances of A and 2 instances of C. So that is what it is requesting. Is it available? Yes, it is available, because 202 is less than 424. If this request is granted, then operating system will have 2 instances of A, 2 instances of B and 2 instances of C. And this will become 0. Okay. This will become 0, right? Okay. See, previously in this step, I want to make one change here. Sorry. Yeah. Let us come back here. when P3 is requesting one resource, you are when P3 is requesting for one more resource, you are giving that one resource. Okay, so from 3 it becomes 2, and one resource you are giving. Okay, so now the allocation to P3 is what? Now the allocation to P3 is 311, 311. Okay, because one resource already you have given, it is allocated. Okay, so after some time P3 will complete and it will release all the resource. So it will become 3 plus 2 5, 1 plus 1 2, and 3 plus 1 4. So the current resource that are available with the operating system will be 524, because it releases 3 resources of A, 1 resources of B, and 1 resources of C. Okay, now we'll have P1. Okay, so P1 needs 202. So if you give 2 resources of A and 2 resources of B, C, then it can be given, because 202 is less than 524. Then it will become 3, 2, and 2. Then it will become 3, 2, and 2. And this will be what? This will be 4, and this will be 2. This will be 4, and this will be 2. Okay. So after some time, operating system will complete executing P1. Okay, and it will release this 4 and this 2 resource. That is 4 resources of 4 instances of A and 2 instances of C. So it will become what? 4 plus 3, 7, this 2, and 2 plus 2, 4. Okay, 2 plus 2, 4, right? Now finally P4 will execute. P4 needs 2 instances of C. So can it be granted? Yes, because 002 is less than 002 is less than 7 to 4. So if its request is granted, then this 7 to 4 will become 722, 722, and this 2 will become 0, because the request is satisfied, and this 2 will become 4, because 2 more resources were allocated, right? Now after some times P4 will complete. When P4 completes, it will release all the resources. 0 instance of A, 0 instance of B, and 4 instance of C. So now finally operating system will have 7, 2, and 6. Okay, so now all the processes has completed its task. So finish of I is true. Okay, so this is a safe sequence. So finally you can check this. There are 7 to 6. It means 7 instance of A, 2 instance of B, and 6 instance of C. So that is the original count available with the operating system, right? So this is how the detection algorithm works. Let us consider another scenario. Consider this scenario. Assume that P2 requests an additional instance of type C. P2 requests an additional instance of type C. That is, P2 becomes 001. No other changes. Previously P2 was 000. Now P2 becomes 001. You can see here. Previously P2 is 001. Now say it is requesting one more instance of C. Instead of 001, it becomes 001. Instead of 000, it becomes 001. Now will the system will create a deadlock or not? If you ask this question, now actually it will create a deadlock, because there is no safety sequence now. P0 will complete. See, in this case also P0 does not need any resource. So P0 will complete and it will release one resource of B. So if it release one resource of B, it is 010. Operating system will have one resource of B. But with this one resource of B, no process can complete. P1 cannot complete, because P1 needs 2 instances of A and 2 instances of C. P2 cannot complete because P2 needs C, 1 instance of C, but OS has 1 instance of B. Okay, P3 cannot complete, P4 cannot complete. So none of their requests will be satisfied. P1's request for 202 will not be satisfied. P2's request for 001 will not be satisfied. P3's request for 100 will not be satisfied. P4's request for 002 will not be satisfied. Only P1 P0 will complete. Only P0 will complete. all the remaining 4 processes will be deadlocked. Okay, because all the resources were held by others. So P1, for example, if you see, P1 is waiting for waiting for two more resources of A and two more resources of B. Okay, two more resources of A and two more resources of C, right? Which is being held by some other processes, which is being held by some other processes. For that, it will wait. Similarly, P2 is waiting for one resources of C, which is being held by other processes. So this state will lead to a deadlock. So now if there is an additional, if P2 requests an additional instance of resource type C, then the system will lead into a deadlock state. P0 will complete, but there will be a deadlock between P1, P2, P3 and P4, right? So this is about deadlock detection. So what we have discussed in the sense, so in deadlock detection case, we allow the system to enter into the deadlock, and then we detect whether there is a deadlock or not. And operating system will frequently run this algorithm to check whether there is any deadlock or not. Okay, so because before going for deadlock recovery, deadlock should be detected. Then only you can recover the deadlock. So this is how deadlock detection works. And there are two algorithms available. One is when the when there is only one instance of each resource type is available, then we use the first type of algorithm, which is a graph based algorithm, which is called as wait for graph. Okay, in the wait for graph contains only process as its edges. So in the wait for graph, if there is a cycle, then there is a deadlock. If there is no cycle, there is no deadlock. So the operating system will frequently run this algorithm and check whether there is a cycle or not. If there is a cycle, it will confirm it as a deadlock. The second type of algorithm will be used when there are multiple instances of each resource type is available. This is very similar to the banker's algorithm's uh, safety algorithm. So this is used to check whether there is a deadlock or not. Uh, so, and then we have discussed with examples how deadlock can be detected uh, with uh, with deadlock detection algorithm. Okay, that's it. Let us stop here.